And correlation is this is one of the few things that we're talking about in basic statistics that's not kind of a mathematical concept. It's also something that's used in general conversation. The idea of correlation, at least anyway, that one thing is associated with another. In other words, a correlation. Um, Generally, if you talk about correlations, you're talking about mathematically, you're talking about numerical variables, two sets of numerical variables. For instance, on this table that we're looking at right here, we have different countries and the cigarette consumption, the average cigarette consumption, and the rate of lung cancer. Okay, and as we can see that for Iceland, the average cigarette consumption was 230 cigarettes per year, and the number of cases of lung cancer. This is probably per 10,000, 100,000. It's a rate. Was 6 per 10,000, 100,000. And in Holland, the cigarette consumption was 490 cigarettes per year, and the lung cancer rate was 24 per. And we can see in general, right, not without any exceptions, but in general, that as the cigarette consumption increased, the rate of lung cancer increased. Not perfect. Great Britain, there was a little bit lower rate of cigarette consumption, but they had a higher rate of lung cancer than they did in the United States. This is 1930. You guys know in the 30s and 40s, there were issues with air quality in England as well, in the major cities, because they used coal burning stoves in the homes and so on and so forth. And like literally, they would have periods when if they had thermal inversion, that the air was literally poisonous. People with respiratory conditions were literally dying from the level of smog and soot in the air that was present in the air from these from all this coal that was burned there. So there are a lot of other stuff going on, but in general, we see an association. More cigarette consumption is the more no cases of lung cancer that we typically get. Bless you. Okay, so now one of the ways to really kind of visualize whether or not there's an association between two numerical variables is to graph it. And the kind of graph that you use is called a scatter plot. Okay, and this is a scatter plot. And this is literally the data that we're looking at here. The cigarettes are on the cigarette consumption, per capita cigarette consumption in 1930 is on the x-axis, and the lung cancer rate is on the y-axis. We also call the x-axis the independent variable. It's the one that's causing at least what we believe is causing an increase in the other. Okay, I'm going to talk about that in just a second. But if we actually looked here at the country with the lowest per capita rate is Iceland, 6 cases per, and we're about to look at it. It's 6 cases per 100,000. Okay, 20 years later in 1950, this is the per capita consumption in 1930, and of course, there's a long latency between exposure and cancer. So they looked at the rate in 1950 as a comparison. But you'll see here that blue dot represents Iceland. Okay, and the United States is up here at 1,320 deaths. So our x-axis we're at 1,300, and our y-axis we're over here at 20 something right here. So each one of these dots represents the x value and the y value, the cigarette consumption and the lung cancer rate. And we can see that in general, that as you increase the cigarette consumption, the number of lung cancer cases go up as well. So now we can see this general rate that this is increasing at. In fact, we could actually draw a straight line that kind of estimates what this increase looks like, or estimates what this where these points lie as far as this increase is concerned. Okay, so one of the things that we're interested in is does it look like a straight line, or does it look like something that starts off slowly, goes up like asymptotic, or does it look like it's flat and straight, or does it look like and next we might be interested in what's the direction of this thing? Is it sloping upwards or is it sloping downwards? Okay, in some cases we may looking at situations where as a value goes up on the x-axis, the value on the y-axis goes down. There's a negative correlation. As one increases, the other decreases. So we may see things like that. We're looking at the strength of association. How close to a straight line, or how close to the line that you can predict, do all these values lie? Does, if you were to draw a straight line, that are the values so that it like kind of like centers, is somewhere in the center of all these lines so they're balanced between the number of values that are above and below it and the distance above and below it. Is that line that gives us the best fit? Are the values that we know, the real values, are they close to that line, or are they scattered around far away from that line? Okay, and also if there's any outliers, if there's some values that just don't seem to make any sense, like in this one, it looks like the USA for some reason could be an outlier here, right? For one reason or another, because it seems like we're getting a lower rate than we would expect among the others. But it could be maybe one of the others, like this highest one, maybe Great Britain, maybe oh sorry, one can't, yeah, Great Britain, right? Maybe Great Britain is a outlier because the level's so high because there's all these other issues between 1930 and 1950 that might be contributing to high lung cancer rates in Great Britain. So maybe that's the outlier, and really the best line fits down here somewhere. So yeah, that's one of the things that we have that's in consideration. So if we look at these two images right here, okay, and if we look at these two images right here, scatter plots, you'll notice that our eye is not a very good judge of the strength of correlation. The reason for that is both of these display the same data, right? This one looks like it's scattered more away from the line. Like this looks like a stronger correlation here, tighter, closer to a straight line. This one looks further away from a straight line. It's really the same data, right? It's just that it's on different scales. The scale is expanded on the top one, expanded on the bottom one, so everything's clustered closer together visually, and it's tightened up on the bottom, on the top one, so they look more spread out. But we don't have to worry about that for right now. We're going to do this mathematically at some stage. The next thing we got to understand about this is that correlation itself doesn't imply causation. I was talking about it as if it did here, right? And that somehow or other cigarette consumption is associated with lung cancer, is a cause of lung cancer. We know that now, right? But there's many correlations that are not causative. They're associations, but they're not causative. For instance, one of the examples we like to use is that the more damage there is due to a fire, the more firemen that are present, right? So, and that makes sense, right? Bigger fire, it's going to be more firemen. Are the firemen causing the damage? Sometimes I've seen some firemen cause a little bit of damage every once in a while. If you have ever seen them at work. However, for the most part, the reason for more firemen is because it's a bigger fire. So although there's a correlation between the amount of property damage in a fire and the number of firemen that respond to the fire, it's not cause. There's no causal effect there. It's not because of the firemen. It's because of some other factor. Okay, but there is a real association. Some correlations may be spurious. That means basically just by chance or whatever. In fact, I'm going to open this up. I think I gave you a link to this on Blackboard. Let me see if I can't get to it. Okay, there's a guy. There's always a guy, but this guy did something very interesting. Let me go into class sessions. I'm pretty sure I put a link in. Well, no. Why did it do that? Did it log me out? Oh, there we go. Okay, good. Okay, I'm going to go in here, and I think I gave you a link here. Corey, yeah, okay, here's the guy right here. Okay, I'm going to open this one right here first. Okay, just a coincidence. The more people eat cheese, the more people are killed by their bed sheets. This guy demonstrated that there's a correlation between the rate at which people eat over many years, the rate at which people eat cheese each year, and the number of people that are killed by their bed sheets. Okay, and he found many other spurious or seemingly like irrational correlations. Guys has a whole web page on. I mean, some of them are pretty interesting. You can take a look at the link later on and get an idea what some of these look like. Okay, let's see what we got. Suicide. He found. Look at the level of correlation here that he found between U.S. spending on space science and suicides by hanging, strangulation, or suffocation. Right? Not likely to be really associated. right? People who drown by falling into a pool and films Nicolas Cage appeared in.
There's a correlation
Right? I mean, look how close. Look how close they seem to mirror each other. Per capita cheese. Look at the one we just looked at. The per capita cheese consumption. Number of people die by strangulation in their bed sheets. Per capita consumption of margarine and the divorce rate in Maine.
Well,
Right there you go. The age of Miss America and the murders by steam, hot water vapors, or hot objects. Now, I'm sure that he looked at many numerical variables that were not correlated, but he just kept looking. If you look enough, you're going to find these spurious correlations. Who knows what they mean? Who knows how many of these are just purely by chance, and how many of these are because there's some unrelated kind of other factor going on here, that certain years when there's a lot of cheese produced, that there's some other thing going on, right, that we don't see the connection here with. But you can take a look at that. It's really pretty interesting. But in correlation, the point here is in correlation, we don't care about causality. We're just looking to prove or show a correlation. Regression gets a little bit different. In regression, if I get a chance, we'll talk about where that name regression came from. But regression is basically a way of quantifying a level of correlation. But it assumes that you do it and you assume when you do it that there is a causal relationship. You want to establish this mathematical relationship between one numerical variable and another numerical variable, so that you may perhaps be able to use that to understand how much of a factor one variable is on another, how important it is in terms of predicting the other. In other words, how, if I know how much a person's how many cigarettes a person smokes per year, how good an indicator of that, or how predictive is that of what the likelihood is of that he will die of lung cancer, for instance. That's important to us because we want to know that stuff. If we're evaluating the causes of asthma, for instance, right, we might want to be interested in what the dust levels are in the neighborhood, the atmospheric dust, the ambient dust levels are in the neighborhood of children who have higher, in neighborhoods where children have higher or lower rates of asthma. We might want to know what the level of roach frass or roach particles are in apartments of children that have different rates of asthma. We might want to know what ozone levels are like when children, if ozone levels in the ambient air are associated with the number of children that show up in a neighborhood for in a hospital or emergency room because they're having an asthma attack. We may be interested in all this stuff, and it's important to us to understand, well, which of these are important factors and which of these are unimportant factors? Which of them are more predictive, right? Because if we're going to try and figure out what the best way to respond to this is, where the best place to spend money or make interventions are, we need to know which are the important factors, which are the minor factors, and that's what regression does for us. And in regression, what we're doing is, you can see it right here, we're attempting to fit a line to the data, and we're